Hi everyone and welcome to the internet. What we're going to be doing in today's physics lesson is having a look at how transformers work. So hopefully by the end of today's lesson you'll know what transformers are and how they're actually able to work. To start us off though, we've got 3 questions based around our previous lesson, so have a go at answering these 3 questions in your book for me. I'm going to give you about 3 minutes to have a go at this. Let's check these answers then. So for question 1, the type of current that we're going to make in an alternator is an alternating current, or AC. So give yourself a tick if you got either of those phrases. The second one in our dynamo would be direct current, or DC, tick for that one. And when we're looking at the difference between their structures, alternators have the coil attached onto slip rings, whereas the dynamo, the coil is attached to a split ring commutator. So if you got that right, give yourself a tick. Add up your score, give yourself a mark out of 3. And obviously you can let me know in the chat window how you did as well. So what we're going to be looking at in today's lesson is this structure called a transformer. Now, we're not talking about the movie or the cartoon Transformers. That's certainly not robots in disguise at this point. We are talking about a very important structure that we use in a wide range of different settings. And the reason that we're going to use this is because a transformer will either increase or decrease the potential difference. And that's really important for us because not every single appliance is going to run at exactly the same potential difference. So for example, something like your mobile phone, you certainly wouldn't want 230 volts flowing straight into that, because trust me, the battery will not do well at that point. So what we need to do is have a much lower potential difference actually going into the mobile phone itself. But the mains, it's all one voltage, it's all 230 volts. What we can see in the bottom right of your screen is a diagram of a transformer. So what we've got is a metal core, okay, so it's going to be an iron core in fact, and you can see that on the left hand side we've got red lines that are our primary coil, and on the right hand side the blue lines, those are a secondary coil. So we have two coils of wire wrapped around the two sides of the iron core. Hopefully one of the things that we do remember from our previous couple of lessons is that we will induce a potential difference when magnetic field lines that are cutting a coil change. So what we can actually do is have three ways that we can change the field lines cutting a coil. First one is we can move the magnet or move the coil. Second one is we could use another coil and turn the current in it on or off. And the third one is we could use another coil with an alternating current. So any of those three things are going to lead to a change in the field lines cutting a coil. So what we need to do is write down the points on the screen at the moment in your books, because the ways that we can change it is important. So I'll give you about a minute and a half to 2 minutes to get that done. If we now look at those three factors in a little bit more detail, just to explain how they work. So the first one that we've said is that we would move the magnet or move the coil. Now that just goes back to what we've talked about previously, that as soon as we're moving the magnet or the coil, then quite clearly the wire is cutting those magnetic field lines. So that one I think we've kind of done to death by this point. The other two though, we're going to have a little look at in a bit more detail. So using another coil and turning the current in it on and off. When we're turning the current on and off in that first coil, then what we're actually doing is changing the number of field lines cutting the second coil, because obviously when the current is on in the first coil, it's generating a magnetic field, and therefore the second coil is crossing magnetic field lines. When we turn it off, then we don't have those magnetic fields being generated by our primary coil, and so it's not cutting those field lines in the secondary. So we can see turning the coil on and off, then that's going to affect it. And our third one there, using another coil that's got an alternating current in it, then hopefully we remember that when we were talking about alternating current, then we were talking about that change in direction. Remember, if it's alternating, it's going from the positive to the negative to the positive to the negative and so on. So if we generate an alternating current for this, then what we're going to see is that constant change in the field lines, because the current is constantly changing direction. So that means the secondary coil is going to then have that change in the field lines it's cutting. So we've got our three ways there that we're getting those changes, which are then going to induce a potential difference in that secondary coil. Make sure you've got those points written down, and obviously if there's anything else you wanted to write down from the explanation, by all means feel free to do so. I'll leave this up here for about another minute to give you a chance. So if we think back to the picture I showed you at the start of the lesson of our transformer, we've got that iron core, so it's a solid iron core. On one side we have an actual coil wrapped around it, and then we've got a second coil wrapped around the opposite side. So what we actually have here is the ability to, for want of a better word, trap the magnetic field inside the iron core. So what we're actually doing is, as the current is flowing through the coil of wire, then it's going to create a magnetic field that's then going to be trapped within that iron core. So we've got a magnetic field right the way around the iron core. What we're going to do then is understand how this phenomenon, if you like, of being able to trap a magnetic field within an iron core with a couple of coils wrapped around it can suddenly allow us to change the potential difference we're generating. Now, what actually happens then is that as we actually put an alternating potential difference across the primary coil, then what we're going to produce is an alternating current in the primary coil. So remember, an alternating potential difference will produce an alternating current. So in our primary coil, we will have an alternating potential difference across that, and that's going to produce an alternating current flowing through the primary coil. As a result of that alternating current in the primary coil, we get a magnetic field within that iron core. And because the alternating current is constantly changing, positive to negative and so on, then what we find is that that magnetic field in the iron core is constantly changing. As a result of that, remember the other side of the iron core has got that secondary coil of wire wrapped around it. We see this constantly changing magnetic field around that wire. We're then going to induce a changing potential difference in the secondary coil. So make sure you've got those 3 points written down just to explain how it works. So the first thing that happens is an alternating potential difference across the primary coil produces the alternating current in the primary coil. That then produces a magnetic field in the iron core that's always changing, and that is going to induce a changing potential difference in the secondary coil. So I'll leave this up for about another minute and a half so you've got a chance to write those points down. So what we can see there is how our transformer works, and it does rely on having this alternating potential difference in the primary coil. Now, one of the ways that if we were to do this experiment in class people mess up is, rather than using the alternating current from the power pack, what they do is they plug into the direct current, the DC terminals. Now remember what we've said, if it's a direct current it doesn't change, it's always the same, so it's always positive, for example. Now that means that if we're trying to create a transformer, it needs this alternating current. So if we had direct current, it won't work. So just look out for that as one of those potential questions they could put on there as to why a transformer doesn't work. If they've said it's connected into the DC terminals, it's not going to work. It needs the alternating current, AC. What you can see on your screen at the moment then is a formula, but good news, it's not one you've got to memorize. Finally, we've got to one that's going to be on that formula sheet in the exam. So what we've actually got here is the actual formula we could be asked to use in terms of our transformers. So what we actually have is the potential difference across the primary coil divided by the potential difference across the secondary coil is the number of turns in the primary divided by the number of turns in the secondary. Now what you could be asked to do is to work out any of those on there. So you've got to be able to rearrange this. Now what we're going to do is have a look at the kind of question we could have. We'll go through a worked example for it, and then I'll give you a chance to have a go at doing your own as well. So example of the kind of question we could have is on your screen at the moment. Your mobile phone charger changes the mains potential difference of 230 volts to 12 volts. If there are 300 turns in the primary coil, calculate the turns in the secondary coil. Let's have a little look to see how we'd actually work out one of these questions then. So type of question we could get is like this. Your mobile phone charger changes the mains potential difference of 230 volts to 12 volts. If there are 300 turns in the primary coil, calculate the turns in the secondary coil. So what we've got there is our key bits of information. So we've underlined, highlighted or circled the key things as we're actually going through it. Now the next thing we actually do is just do yourself a quick sketch of your transformer. Now this is literally what I mean by a quick sketch of a transformer. There we go, we've got two sets of coils. You can kind of see that, I hope. Now what we're going to do is we're going to label those key features we know on here. So we're going to start off with our potential difference of 230 volts. So that goes on the left hand side, that's what we're starting with. And on the right, we know we're going to have a potential difference of 12 volts. So we can put that one in. Then we obviously need to know how many turns are on the coils. So we can put our little ends underneath, number of turns on our coil. And from the question, we can see there are 300 in the primary. So the primary is on the left. That does say 300, honestly. So we've got 300 on the left, and we don't know the one on the right. So we then need to go back to our formula, but we need to rearrange it, because what we need to do is make the number of turns in the secondary coil the subject. So what we're actually going to have is the number of turns in our secondary coil, and when we rearrange that, what we're going to find is it's the potential difference in the secondary coil divided by the potential difference in the primary coil, and we then multiply that by the number of turns in our primary coil. Okay, so that's how we'd rearrange this one. Then what we're going to do is substitute in those values. So potential difference in the secondary is over here. So we've got 12. We divide that by the potential difference in the primary, 230. So 230 there. And then we're going to multiply it by the number of turns in the primary, which was the 300. So once you've got that, we're then going to get our calculators and we're going to work it out. So 12 divided by 230, and then we times that by 300, and we come out with an answer of 15.65 and lots of other numbers, and it goes on. But because we're looking at the number of turns we need, we've got to have a whole number. So that means we've got to round that one up. So we would therefore need 16 turns on our secondary coil. And that's how we do it. Okay, so we've seen the worked example. Now your turn to have a go. Very similar question here. I'm not going to ask you to do any further rearranging at this point. So just following the same procedure we did in the worked example, have a go at this question in your books. And don't forget, you are always allowed to use a calculator in a science exam. So hopefully you've got your calculators handy to be able to do this. If you don't have your calculator handy, at least you can show the working. And this is something that is very important to do in any calculation question, which is to show your working. Because that way, even if you make a silly error typing a number onto your calculator or copying the number from your calculator onto the paper, you still can pick up a number of the marks. So show your working, have a go at working this one out for me. I'll give you a couple of minutes to have a go. Okay, so when it comes to solving this one, what we're going to do is 24 divided by 230 and then multiply that by 400. Now if you put that into your calculator, you come out with an answer of 41.739 and loads of other numbers. And what we need to remember, of course, is it must be a whole number. So because it's 41 point something, then we'd need 42 turns on the coil. So if you got that right, give yourself a tick. You can get more than one mark for this kind of question. So if you got 24 divided by 230 times 400, give yourself a tick for that bit. And then if you got the 42, you get a tick for that. So it's out of 2 this one. Give yourself a mark out of 2. The last thing we need to know then is that when we're talking about transformers, we've got 2 types. We've got step-up transformers and step-down transformers. Now the key difference between these is what they do to the potential difference. So a step-up transformer is going to increase the potential difference, whereas a step-down transformer decreases the potential difference. So the kind of hint is in their name there. So step up increasing, step down decreasing. And the way they do that is by changing the number of turns on those coils. So the StepUp transformers actually have more turns on the secondary coil than they do the primary. So that means we're going to increase the potential difference. Whereas the StepDown transformer, they have more turns on the primary coil than the secondary, so it will decrease the potential difference. So make sure you got those points written down. If you really want to do the little sketches of the diagrams at the bottom, you are more than welcome to do so. I'm just going to leave this up here for about another minute or so, just to give you a chance to get the 2 points in your books. Final thing for today then are the plenary questions. So 3 to have a go at today. Obviously show your working in your books for the calculation one, and don't forget you can always get the answers and mark your work later on from my website. So everyone have a go at doing these. I'll leave them up here for a couple of minutes for you. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.